This one's kind of an oddball. It's the integral from negative pi over 3 to pi over 3 of x to the fourth times the sine of x dx. This is an oddball because it involves no composition at all. I note that the interval is symmetric with respect to 0. That is, negative pi over 3 is to the left of 0, and pi over 3 is to the right of 0, and 0 is in the middle, right? So it's symmetrical. And this matters because the integrand, x to the fourth times the sine of x, is an odd function. Neglecting x to the fourth for a moment, if I look at y equals the sine of x, and just a portion of the graph, on an interval that's symmetric with respect to 0, then the amount that's above the x-axis on the right is the same in size as the amount that's below the x-axis on the left of the y-axis. In particular, if we're looking at, say, pi over 3 and negative pi over 3, we can see that the positive region to the right of the y-axis is exactly offset by the negative region to the left of the y-axis. And if I take that negative value and add it to that positive value, I'm going to end up with a 0. So folks, if I have a symmetric interval and an odd function, and when I say symmetric interval, I mean with respect to the y-axis, then the answer is going to be 0 every single time. And that's it. Now we have another one that's, I think this is weird, but it's weird in a different way. We do have a composition. So I have the integral of x times the square root of x plus 2 dx. And what I'm going to do is I'm going to identify the inside of the radical. So as my u is equal to x plus 2. And so du is equal to dx. Now that's a little weird there because I can replace dx by du. Okay, fine. That doesn't do anything to replace the x out front here. Go ahead and rewrite the integral. And let's write down what we have here. This is the square root of x plus 2 becomes the square root of u. And I'm going to need some more room here, I can tell. Now we're kind of stuck because I have this x sitting here and I don't know what to do with it, but check it out. If we take this equation, u equals x plus 2, and solve it for x, then we get x is equal to u minus 2. So then x gets replaced by u minus 2. It's a little bit different, right? Now, I can't integrate a product, but I can distribute that square root of u. So this becomes the integral of u to the 3/2 minus 2u to the 1/2. Went ahead and expressed that as an exponent so that I can more easily apply the power rule. And so u to the 3/2, add 1 to the exponent, becomes u to the 5/2 divided by the new exponent, 2/5 out front here, minus. U to the 1/2 becomes u to the 3/2, and then divide by the new exponent, so multiply by 2/3. There's already a 2 up front, so that becomes 4/3. And then we have plus our constant of integration. But u was x plus 2. I need to bring it back to the original variable because this is an indefinite integral. So my answer is 2/5 times the quantity of x plus 2 to the 5/2 minus 4/3 times the quantity of x plus 2 to the 3/2 plus c. And now I'm going to give you a chance to practice that on your own. We have here the integral of x squared times the square root of 2 plus x dx. See what you can do with it. Try to finish it. Come back when you're done. With the substitution u equals 2 plus x, I solve for x and I get x equals u minus 2, and du is equal to dx. X squared is then u plus 2, the quantity squared. The square root of 2 plus x becomes the square root of 2, and dx becomes du. Foiling the u plus 2 and distributing the square root of u, applying the power rule, and then back substituting u, replacing that with 2 plus x, gives us 2/7 times the quantity of 2 plus x to the 7/2, plus 8/5 times the quantity of 2 plus x to the 5/2, plus 8/3 times the quantity of 2 plus x to the 3 halves plus our constant of integration.